Good morning all. So today we are going to discuss about the module 4 content, that is about point source and point array, and how this particular antenna works with respect to point source or with respect to a radiating element. Okay. So before entering to that particular field, let us discuss about on what particular area or what particular range your antenna will work. Okay, in which particular point, what is that zone, how many number of zones, and with the help of those zones, what are the features will come into picture, that we will see. Okay, now in this figure you can see there is one radiating element, a small antenna type element is there, and above around that antenna one dark line and one dotted line is there. Okay, now these lines are nothing but a distance, these lines are nothing but a zone. Within that your radiating fields are going to be measured. Now as we know that height of the antenna matters. If the height of the antenna is less, your wavelength is going to be less and the frequency component is going to be very high. So as much as the dimension of that element is less, it can operate at a higher frequency. And if it is work for a longer distance communication, we require a frequency component to be high. So if a frequency component is to be high, that means my antenna height plays a vital role. So the relation we can form like that: the height of the antenna, or this D, is inversely proportional to the wavelength or the measuring distance, but where we are measuring the, suppose my point is available at this point, at this point, at this point. Let us consider point 1, this is point 2 and this is point 3. So as the distance increases, your wavelength must decrease, so that frequency can reach to a maximum distance. Okay, so we will form certain relation through which the measurement distance, it will form as a inversely proportional to the wavelength. So as much as the distance increases, your wavelength must be less, so that frequency component must be very high. And we will see that in which particular region what are the changes are going to be identified, whether the electric field and magnetic field are both in phase, or it is perpendicular to each other, or patterns are changes, or patterns remain as it is. So that thing we are going to discuss in this particular class. Okay, so here you can see in this circle, basically there are three regions are identified. One region is within this particular circle. Okay, that is first region 1. So here I will mention this is region 1. Okay, then outside of this circle, between the dotted line and the constant circle or the constant line, it is a region 2, and outside of this dotted line is a region 3. Now what this region name called? First one, the first region is called as our reactive near field region. Why it is called near field? Because the radiating antenna is having a certain range at which the patterns will be generated. If I am measuring the element as nearer to the radiating element, suppose this is the radiating element, and within this R1 if I am going to measure that what is the component of electric field, what is the component of magnetic field, and how much power is radiated, that means we are seeing within this particular region, and that region is called as a reactive near field region, or you can say it is called near field zone, because this is one zone, this is one zone, and this is one zone. So these are the three basic zones are available for any sort of radiating element, but with respect to the radiating element the features will change. In the near field, here the variation of electric field and magnetic field, there are three basic zones are there. One is reactive near field, one is radiating near field, and one is far field. So reactive near field is quite near to the radiating element, and the radiating far field is outside of this particular one, which is greater than R1. This R1, R2 is having a relationship with respect to the dimension of antenna and the wavelength. Okay, so radiating near field region means in this second region it is called Fresnel region. Okay, and outside of this region it is called as a Fraunhofer region. Now this all thing comes into picture when we are discussing about optics. Wavelets are formed continuously, Fresnel regions are there and Fraunhofer. According to that we have considered for this also, but we have to form relation with respect to dimension of an antenna, wavelength of an antenna, and the distance of an antenna, distance of the measuring point. Suppose my point is at P1, P2 and P3. If my observation point is P1, that means I am in a region 1. That is called reactive near field zone. If my point is P2, that means it lies between two regions, first region and the third region. So first region is a reactive near field zone and the third region is a radio far field zone, or it is also called as a Fraunhofer zone. And this region, in this what are the changes are there, let's see. So as I have written reactive near field zone, in this E and H are out of phase but 90 degree perpendicular to each other, out of phase but 90 degree perpendicular to each other. So in this the radiating element must be orthogonal to each other but in phase. That means it is asking that it says that when we are measuring the intensity of any electric field or magnetic field within this first zone, the variations are very less. Variations are cannot be means it is so much high that what is the electric field and magnetic field both will be in out of phase and as well as perpendicular to each other according to the direction of propagation. But as much as the distance increases, this variation of electric field and magnetic field out of phase will not change. It will in phase but 90 degree orthogonal to each other, and it is propagating perpendicular to the direction of wave or direction of a particular power flow. Okay. So here in this zone, this R1 is have a relation that is 0.62 times of root over of d cube by lambda. So here this R1 I can write as 0.62 root over of d cube by lambda. So d cube, d is the dimension or the length of this antenna. If I will say length is lambda by 2, that means your d is lambda by 2. If d is equals to lambda by 4, that means it is quarter wave dipole. If d is equals to lambda by 8, then you have to substitute in place of d as a lambda by 8. So d is the dimension of an antenna and lambda is the operating wavelength in which it is working, and this wavelength is inversely proportional to the frequency. So if you form a relation lambda with respect to f, your distance is going to be related with respect to f. As much as the distance increases, the frequency component requirement is also increases. So this particular relation will help us to judge for a long distance communication how much frequency we are going to use, and for short distance communication how many what is the strength of the frequency we are going to use. According to that we have to judge whether for a long distance what is the frequency, for short distance what is the frequency, and with respect to this particular zone. So this is the first, it is called as a reactive near field zone. Next one is the second zone. In this zone it is called as a radiating. In this zone it is radiating. Okay, electric field and magnetic fields are radiated in this particular zone. Unlike to the far field region, the radiation pattern varies. Okay, so radiation pattern will vary in this particular zone. Electric field and magnetic field will be in phase but perpendicular to each other and also perpendicular to the direction of propagation. Okay, in this particular zone your R2 maximum value will be 2d square by lambda. So 2d square by lambda, these are the standardized calculative value. Only to identify these zones we have identified with a certain ranges. If R1 is identified, that means it discusses about the reactive near field zone. If R2 is discussed, that means it is called as a Fresnel zone. And if it is distance is R3, which is greater than 2d square by lambda, means R3 means this outer one, then it comes under our Fraunhofer zone. So in this Fraunhofer zone, the large distance from the radiating element, yes, it is a large distance from the radiating element. This is the radiating element and this is the observation point, so it is a large distance. So if it is a large distance, your wavelength must be less and the frequency component must be very high. Radiation pattern does not change shape as the distance increases. Remember that if the distance of observation increases, radiation pattern will remain constant. Okay, it will not vary. The shape will remain as a donut type. If you are considering with respect to sine wave, if it is considered with respect to cosine wave, the pattern will change. That we will see now. So radiation pattern does not change the shape as a distance increases. So this is the most important point. If the distance increases, the radiation pattern remain constant. But the electric field and magnetic field are in phase but perpendicular to each other, orthogonal to each other. Okay, and perpendicular to the direction of total wave propagation. Total wave propagation means the electric field and magnetic field combinedly, when it is projected in a certain direction, with respect to that direction, electric field and magnetic fields are perpendicular to each other. Okay, and what is that particular distance? Your distance must be greater than 2d square by lambda, because R2 is having, it is 2d square by lambda. So if it is greater than this distance, then it is enters to the Fraunhofer region or Fraunhofer zone. So basically your antenna will work whether you consider loop antenna, whether you consider helical antenna, whether you consider this dipole antenna, short dipole antenna, whatever it will basically distribute in this particular three region. First is near field reactive region, reactive near field region. Second one is the radiating, which lies between first region and third region, that is our radiating near field region. And the last one is called as our far field region. And basically whatever the measurement we are doing, practically we are doing in terms of far field region only. At a longer distance we are measuring the effect of the intensity of the radiating element. Okay, so always remember that whenever we are measuring the intensity of the radiating element, we are considering with respect to the far field analysis. So far field means it is a Fraunhofer zone. If it is a radiating near field zone, means it is called as a Fresnel zone. And if it is near to the radiating element, then it is called reactive near field region. Okay, with the help of this sort of assumption, we are going to discuss about the point source and the array of point source. And according to the point source, what are the radiation pattern, what are the power pattern, what are the field patterns, that we are going to analyze today. Okay. Okay. So this is our point source. So we will discuss on this point source. If the point source is a radiating element, then what are the features are going to be identified, how that field patterns are going to be identified, and how the power pattern is also going to be identified. Now before entering to this discussion, let me clear it off regarding this point source. This point source is a fixed point. Okay, fixed volume you can consider. It is small point from which the radiating energy will come out, and that energy is represented either in terms of pattern, power pattern, or the field pattern. If it is with respect to field pattern, means electric field and magnetic field in a certain direction we have to identify. Now previous class I have shown that if the radiating element is this, a donut structure will be formed with respect to that radiating element. If it is with respect to sine, then the donut form will be there. If it is a cosine, then it is a circular form will be there, up and down. That we will discuss now. Now in this particular figure you can see a radiating element is a dot. I have identified that particular element as a fixed point with a certain volume is a dot, and it is placed at the center of the observation of this circle. Now these two circles, it is shown with respect to the regions what we have discussed now. One is the near field radiative region, reactive near field region. Second region is called as our Fresnel region, and the third region, which is the far field region, it is also called as a Fraunhofer region. According to the distance we are going to measure. So basically the variation of electric field and magnetic field is very less when we are measuring at the far field. Okay, so whenever we are going to measure some points or measure some intensity, basically we measure at a far field positions. Okay, so here you can see the inner circle is having a radius small b and the outer circle is having a radius capital R. And this capital R is comes under that Fresnel region, that is 2d square by lambda. R is must be less than equals to 2d square by lambda. If it is greater, that means it enters to the third region, which is called as a Fraunhofer region. Now let us consider the observation points. This circle is called as an observation circle. In this circle we have to identify a certain point and we have to measure the fields. So let us consider the point Q is the observation point on the observation circle, and your consideration is that point source lies at the center of the or you can say center of this observation circle. So this is the center of the observation circle, noted as point O, and the point Q is measured. So if it is at a near field region, for the measurement, if I am going to measure the intensity of the fields, either electric field or magnetic fields, that means I have to discuss with respect to the far field region. Why? Because in near field region there is a variation of electric field and magnetic field, and basically when we are measuring all these sort of fields, we ignore to measure in the near field zone. So here I have written field variation due to which we are ignoring the measurement. So in which particular region we will measure? Either with respect to Fresnel region or with respect to the Fraunhofer region. So first, wave originate from the fixed volume emitter at the center of the observation. So from this point the energy will spread. So that is called as a wave. So wave will originate. So either it is in a form of electric field or magnetic field, both. And it will form in a particular electric fields are moving in a radial in nature and magnetic field will be in a circular in nature. Next, so this is the observation point. At this point we are going to measure. So we are going to measure in which particular region? Either in terms of Fresnel region or in our Fraunhofer region. Basically we measure all this intensity in the far field, in which the variation of electric field and magnetic field is very less, at which the wavelength is also very less, but frequency component is very high. So we can extract more information from the far field regions. Okay. Now there are two cases are there. Two cases means if the observation point or your center of the means point of observation in which antenna is placed. So what will happen? And suppose if that particular antenna change the position to certain distance, then what will happen? Okay, with respect to the measurement at a certain far field region. Now in case 1, the center O coincide with the center of the observation circle. First case, the center of the observation circle is O, in which I have placed the antenna, and I am measuring the intensity at the far field region. Okay, that is the first case. Second case, at the point O I have shifted to certain point P, okay, at a small distance D. Okay, so if I am changing the position of that antenna, the observation point at the Q, what effect it will be there? The thing is that if the Q lies at far field, if you change the position of this antenna also, the field variation will be very negligible. But the condition is what? We should measure the intensity at the far field, not at the near field. If it is a near field, that means the effect will come into picture. How? Depend upon this D. If D value is 0, okay, if D value is 0, if there is no change, means this particular point, the phase shift is very negligible. Phase shift between E and H, out of phase as I have discussed 90 degree, so E and H is very negligible. But if you change the position, of that antenna from O to P, that means the phase shift will increase. So as much as this distance D increases, your phase shift is going to be increase. Okay, so these are the two basic points you should remember, that if D is equals to 0, we will see the minimum phase shift. Okay, minimum phase shift of between what? Electric field and magnetic field. But if you increase this distance, suppose if this D increases and with respect to point Q, observation circle, then your phase shift will come into picture. Okay, and this phase shift will disturb the radiation pattern or the intensity what we are measuring at a far field is distorted. So what is the how to overcome this? The overcome of this particular case is that we should measure the point or the observation point, this Q point. The Q point should be placed at a certain distance at which the effect will be very negligible. So where I will put this Q? I will put this Q in a far field region. So my condition must be what? For far field, R must be greater than D. That is the first. So R must be greater than D, very greater than D. Okay. Next, R must be very greater than B. B is this inner circle radius. That R is very greater. That means R we are measuring in the far field, not at the near field. Near field radius is B. Far field radius is capital R. So R must be greater than capital D. R must be very greater than capital small b, and R must be very greater than lambda. So this is the most important factor which help us to identify when we are dealing with the far field measurements. So if there is a change, of position of antenna with respect to the center of observation circle, the radiation pattern may not change, but the condition we have to put that your observation distance R must be very greater than with respect to small b, very greater than with respect to wavelength, and very greater than with respect to small d. There is a change of position. Small b is the radius of a near field region. Okay, so this is the condition through which we can overcome this particular fault. That if the change of position is there, that means phase shift will be there. But if you identify the distance at a longer distance, the phase shift will be minimum. We cannot observe there is a phase of that, because at far field variation of electric field and magnetic field is very negligible. It is only varies when we are considering with respect to near field source. Okay, so this is the case through which the point source can be analyzed. If it is changed with position, if it remain as a center of the positions. Okay, now we will see how this power pattern will come into picture, how this power pattern is generated. Always remember that when I am discussing that donut structure, the donut structure is in a form of a spherical. So whatever the radiation pattern we are going to discuss, all we are going to discuss in terms of spherical coordinate. Okay, so here I have drawn the three-dimensional structure of a sphere in which x, y and z. These are the three axes at which center O I have placed that antenna. That point source is placed at the center of O. Okay, and I want to measure at a certain distance r. What is the effect? Let us, the point is P, and if I am identifying the point on the sphere, the point will be identified with the three dimensions. One is the radius of a sphere, one is the angle theta, and one is the azimuthal angle that is phi. So if you rotate this sphere, your azimuthal angle will come. But if you come from top to bottom of that sphere, then theta will come. And if you take from center of a sphere to outside the curvature of a sphere, then that distance is called as a radius. So here I have mentioned radius, theta and phi. And point of observation is r, theta and phi. So at this point we are going to measure the intensity. But how we are going to measure the intensity? When we are discussing with respect to electric field and magnetic field, the power is related with respect to the cross product of electric field and magnetic field, and that vector is called as a Poynting vector. So whenever the power come into picture, that means we have to consider the Poynting vector. According to that vector only we comes to know in which particular direction my power is going to be flow, or power is going to be radiated, or power is going to be observed at which particular direction. Okay, so for that some observations are there, means consideration we have to take that energy must be streamed radially. That means energy must be propagated radially. So here the first consideration, whenever we are measuring the intensity, we say that at a certain point, the observation point at which intensity is measured, so it is a radially outward. So here you can see it is radially outward. So it is radially outward. Okay, Next, the point source and the pointing vector. Let the pointing vector is S. Okay, you can write P also, capital P, but here I have written S. Has only the radial component. Yes, we have only the radial component because we are measuring the intensity at a certain point in R direction, outside direction. Okay, so here the only the component will exist, that is SR, because this S is having three components: SR, S theta and S phi, depend upon the point. Okay, but since we are considering that energy is propagating radially outward, that means only the vector will have the R axis value. Theta and phi both will be 0. So SR, S suffix R is the vector component of pointing vector along R axis or R direction, you can say. And S theta, S phi both will be 0 because here we are considering that energy is propagating radially outward. Energy stream radially. Okay. For that reason I have written S suffix R, and other factors are 0. There is no variation. Next, what is the magnitude of this vector? The magnitude will be S suffix R, that is the magnitude. But how this S suffix R is going to identify the pattern? Let's see. In this circle, you can see this is called as a polar pattern of isotropic antenna. Now why I am telling isotropic? Because at the point O or the origin point, I have placed that antenna element, point source. Due to the point source, it will radiate the energy in all the direction. Okay, in all the direction it will radiate, and if an radiating element radiates in all the direction, then it is called as an isotropic radiating element, and that radiating element is called as an antenna. Okay, so it is isotropic in nature, means in all the direction the radiating fields are there, but we are measuring at a certain distance. That means we have to see that which component is along that particular direction. So S suffix R is only one component which is along that particular direction. Okay, so source radiate the energy in all the directions, so it is called as an isotropic antenna. Okay, pointing vector independent of theta and phi. Yes, because it only depend upon the radial component S suffix R, and it is independent of theta and R. Okay, next, S suffix R is a constant R as a function of theta called as a power pattern. Now theta is equals to 0, we have seen, and phi is equals to 0, only the SR component is there. But when we are measuring this R component, you can see R is related with respect to theta. So your S suffix R must be a function dependent on theta terms. Then it is called as our, if theta varies, your SR position will change. SR will remain constant throughout the circle, but if the angle changes, this SR means this radius remain constant, but the position will change, okay, according to the angle. So SR must be the function of theta. So here I have written SR at a constant R is a function of theta terms. Okay, so using this concept we can identify the radiation patterns. Okay, radiation pattern, power pattern and relative power pattern. How? Let's see. Here you can see there are 4 figures I have drawn. First, these 2 figures are represented in terms of power. Okay, represented in terms of power. So if it is represented in terms of power, it should be represented in terms of power vector. So power vector is what? S. So S is represented and it is having certain beam width and it is having certain pattern whose maximum value is obtained at theta is equals to 0 degree, and it will change with respect to the lobe. Now here I have drawn a circle, but here I have drawn a sphere type, lobe type. Why? Because depend upon the nature of that antenna, the lobes are identified. The major lobe and minor lobes are identified. When we are considering the power pattern, in that case it will be a circle, means electric field and magnetic field both it will take as a square term, and the total will be a circle component, that I will discuss now. But for the time being, if it is a radiating element is propagating the intensity in a particular direction. So in a particular direction, if the energy is propagated, so in that particular direction maximum energy we are identifying. So this is the direction in which the maximum energy is transmitting. So this is the radiating point. Let us consider this is point O, which is the radiating point, and it is radiating in a particular direction. So particular direction means this is the particular direction. And when we will have the maximum energy, when our theta is equals to 0 degree. So here I have mentioned theta is equals to 0 degree. This SR will have the maximum value. Okay, so SR maximum is, I have written SR suffix M, S suffix Rm. So S suffix Rm is the maximum value of this SR component. What is SR? It is the power pointing vector along radial component. Okay, so this is first, this is the power pattern. Relative power pattern means we have to measure the intensity. We have to form a ratio between the SR component and with respect to the maximum of SR component. So here you can see I have put 1 because I have divided this SRM with respect to each component. So first is SR suffix M divided by SR suffix M, the maximum value will be 1. And next here, this radial component which is identifying the rest of the lobe, it is SR suffix SRM. Similarly, intensity also we can identify with the help of this power pattern, because last class we have discussed how that intensity is related to the power, average power. So it is R square into P average. If you multiply, your intensity will come into picture. So here radiation intensity at theta is equals to 0 degree will have the maximum radiation value, intensity value, and when theta is not equals to 0, then we will get our U. It will change, okay, but maximum at theta is equals to 0 degree, as you can see the maximum value, okay. So next one is the relative radiation intensity. Relative radiation intensity means you have to take a ratio between intensity divided by the maximum intensity, and this point will become 1 when theta is equals to 0 degree. So these are the patterns, or these are the representation of the field pattern or power pattern or intensity of a radiation intensity pattern for a point source. Okay, for a point source projecting the energy in a certain direction, maximum. So this radiating element is projecting the maximum energy in a certain direction. Always remember that this antenna works at a these are the radiating element, and in a certain direction its energy will be maximum. So that maximum energy is called as a major lobe, and the minimum energy distribution is called as a minor lobe. So here we are considering only with respect to the maximum intensity projected in a particular direction. Okay, so this is the basic concept behind our point source. Now we will discuss the different cases, what will happen and how these radiation patterns are going to be analyzed. Okay. So next we are going to discuss about the power theorem, through which we can analyze the radiation pattern for power as well as for individual signals. Okay, either with respect to E field pattern, with respect to H field pattern, or power pattern. So first we will discuss with respect to power pattern, then we will discuss with respect to the field pattern. So for the power pattern, we have a theorem called Poynting theorem, or it is also called as a power theorem. Done. So Poynting theorem basically states that average power crosses through a particular cross section indicates the total power flow from that whole volume or from that whole cross section. So P is the total power, and we have considered S is called as a power vector, Poynting vector. So that vector into ds, if you multiply, the total power can be identified, which is crossing through that cross section. Okay, whole cross section. So power vector is uniformly distributed throughout the cross section, and if I am considering a small elemental area from that cross section and integrate it, the total power can be easily calculated. So P is equals to surface integration power vector into ds. Now what is our S? S we have considered that it is as the radiating element radiates the intensity in a particular direction, that is along R direction, so it is SR dot ds. Okay, so SR is the magnitude of SR dot ds. Now what is this ds? Now we have to see in which particular direction the wave is propagating. Now for this a simple technique is there. Suppose this is the curvature of a sphere, okay, that sphere, and this is the imaginary Gaussian surface. Let us consider point P, and my radial component is along AR direction. Means my intensity is propagating in this particular direction. So for this small elemental area, so this is my ds. So ds along AR. So which two component will be multiplied? Theta and phi. So here I will put r square sine theta d theta d phi. So my elemental surface will be this much, because my vector is propagating along r direction. So imaginary surface which I am going to consider, that is r square sine theta d theta and d phi. And this sine theta d theta and d phi, already we have seen it is called as a solid angle, d omega. Okay, so that also we will see. So what is P? P is the radiated power. What is S? S is the average Poynting vector measured with watt per meter square. And what is ds? It is r square sine theta d theta d phi and measured in meter square. If you multiply only this much component, sine theta d theta and d phi, it gives you a that solid angle, that is d omega. So r square into d omega, it's become as a surface area or cross section. Okay, now once this Poynting theorem is identified, next we have to see on which particular point we are going to implement. Means for point source, because here we are discussing about the point source. So if it is a point source, that means it must be an isotropic source. But practically isotropic sources are physically not realizable. Practically for theoretical discussion, isotropic is fine, maximum value we are getting, but practically isotropic is not possible. Okay, remember that. So if it is an isotropic, you can consider isotropic as a reference value. Okay, but practically these values will change. So for isotropic source SR, so P is equals to how much? Surface integration S suffix R into ds. In place of ds, substitute this value, r square sine theta d theta d phi. So if you are substituting, and if you put a range of theta as 0 to pi by 2, and theta lies between 0 to pi by 2, pi, and phi lies between 0 to 2 pi in all the direction. Okay, if you substitute this range and if you integrate it, you will get 4 pi. So you will see SR dot 4 pi r square. So total power is equals to SR into 4 pi r square. Now what is SR? SR is the Poynting vector, which is along which direction? R direction. We can consider P divided by 4 pi r square as an SR term. So magnitude of SR is the Poynting vector measured in a certain range at a certain point, whose unit is watt per meter square. Okay, now once this power is known, you can easily identify the intensity also. So how to measure the radiation intensity? The radiation intensity unit is watt per steradian. Watt per steradian means it is power divided by the solid angle, P divided by omega. So that is our intensity. So what I will do, my intensity value is r square into steradian SR, means this power divided by the solid angle. As you can see, P is equals to SR into 4 pi R. Okay, so this 4 pi R square, it is 4 pi R square. So if you divide this P divided by 4 pi, you will get a particular answer, that is called radiation intensity, power divided by the solid angle. And which is left out? R square into SR. So R square into SR, which is equals to P by 4 pi, which is nothing but radiation intensity. So radiation intensity can be represented in terms of Poynting vector, which is aligned in terms of R direction. So intensity is equals to R square into SR. Now basically SR is nothing but the average power propagating in certain direction. Okay. So P is equals to, as we have a relation that u into d omega, in place of d omega substitute sin theta d phi, u into d omega, where d omega is sin theta d phi. If you solve this, you will get your solid angle. Multiply with your intensity, you will get your radiated power. So this calculation we have seen in our previous discussion, but with the help of this power vector also we can identify. Now using this assumption, there are four basic cases are there. 4 or 5 basic cases are there through which the radiation pattern can be identified, as well as the directivity can also be identified, because in the previous discussion we have seen that SR divided by SRM, U divided by UM, these are the relative power pattern we have identified, and relative intensity pattern also we have seen. So if you divide these two components, you will get your directivity. Simple. Okay. So how? Let's see. The first case is source with unidirectional cosine pattern. Unidirectional cosine pattern means only in one direction my cosine pattern will be there. Cosine means it is a circle. So this is the cosine pattern, cosine power pattern, and it is having a maximum value of 1 at theta is equals to 0, and this 0.5 you can see, this is called half power point. Okay, this is called half power point. Now with the help of this, my intensity is um cos theta. That means my power can be calculated in terms of cos theta. You have to see that your radiation intensity is in cosine pattern, so that power can be easily calculated. So what we have the relation, power is equals to u into sin theta into d theta and d phi. In place of u, you have to substitute cos theta and d theta. And what is the range of theta and phi? Theta range is 0 to pi by 2, only perpendicular. One angle is that 0 to pi by 2. Okay, and phi is the azimuthal angle 0 to 2 pi. So this angle you should keep in mind, that if it is a cosine pattern, what is its range? If it is a sine pattern, what is its range? So it is unidirectional, means only one pattern is there, and theta lies between 0 to pi by 2. Okay, so 0 to pi by 2, and phi lies between 0 to 2 pi. Now using this condition, substitute in this equation. I have substituted P is equals to u into d omega. In place of d omega, substitute sin theta, d theta and d phi. In place of u, substitute cos theta. Now this is simple integration. Cos theta and sin theta is there. Multiply 2, divide 2, you will get sin 2 theta. Integrate that sin 2 theta, you will get cos 2 theta divided by 2. So that 2 will be multiplied, it will become as a 1 by 4 term. Substitute this range, you will get pi into u suffix n. So this is the total power for unidirectional cosine pattern. Okay. Now we will form a relation with respect to isotropic form. If the point source, this is the point source, if it is isotropic in nature, means in all the direction if it is spreading the energy, then what will be the directivity? According to that we have to see. So point source we have P whole into 4 pi u naught. So here I have written for isotropic P is equals to 4 pi u naught. U naught is the reference value. Okay. At theta is equals to 0 degree, we are having u naught value. And um is the maximum value present in our intensity. So maximum by the reference value, if you take a ratio, you will get the directivity. So here the power is pi into and the isotropic power is 4 pi into u naught. If you divide this by u naught, you will get your directivity. Okay. So directivity is equals to by u naught, that is 4. Why we have identified this? Because anyway the source is an antenna. Antenna is having certain features. What are the features? Intensity, directivity. These are the basic features of an antenna. If it is compared with respect to isotropic antenna, we are getting the directivity. So directivity is the maximum intensity with respect to the given radiation intensity. Okay. So this is our relation, and with the help of this, for the cosine unidirectional pattern, the maximum directivity is 4. Okay. Remember this. Now if the same thing, cosine pattern, but it is a bidirectional. Bidirectional means upper part will be one wave, lower part will be one pattern will be there. If it is bidirectional, your directivity will be half directly, because two patterns are there. For one pattern it is 4, for two pattern it will reduce, the directivity will reduce. So directivity is equals to 4 by 2, that is equals to 2. Remember that. Okay. Next we have source with the sine pattern. Now in place of this cos theta, you substitute sin theta. Okay, and sin theta means it is a pattern will look like this. It is a sinusoid pattern. That this pattern we have already seen in our previous discussion. So here I have substituted u is equals to sin theta. Same procedure. Substitute p into surface integration u into d omega. In place of u, substitute sin theta. In place of d omega, substitute sin theta d theta d phi. You will get sin square d theta d phi. Sin square theta can be written as 1 minus cos 2 theta divided by 2. It is a simple integration. After integrating, substitute the values. You will get around pi square into So pi square into again we have to take with respect to the isotropic antenna, form a relation with respect to directivity. So directivity is nothing but maximum by the given intensity. So here we will get 4 by pi. If you solve this, you will get 1.27. So that means it indicates that if it is a sine pattern, if it is a sine power pattern, then your maximum directivity will be 1.27. Okay. So remember that source with sine power pattern, directivity will be 1.27. If it is a cosine pattern unidirectional, that means it is 4 directivity, and if it is a bidirectional, the directivity will be 2. Okay. Similarly for sine square, now if the sine pattern, if it is square, similarly cosine square also you can consider. So sine square means your value will be sine square theta. So in place of sine theta, it is only square. So if it is sine square, same procedure followed up, identify the power, compare with isotropic antenna power and form a relation for directivity. So what I have done, P is equals to surface integration u dot d omega. U is now sin square theta, sin theta d phi, and we will get 8 by 3 into pi into You equate this one with respect to the isotropic value, you will get your directivity. So directivity you will get 3 by 2, whose value is 1.5. So if it is square, then your power pattern will be, directivity will have 1.5. If it is not square, your directivity will have 1.27. Okay. Similarly for cosine square also you can try. For that you try for cos square theta and identify what is the directivity. Okay. So next class we are going to discuss about the field pattern. This is with respect to the power pattern. So power pattern is analyzed with respect to the power theorem, and that theorem is identified as a Poynting vector theorem. Okay. So using these concepts we can proceed for field pattern in the next class. Till then, practice all those things. Thank you all. Okay, since we have a few more minutes, so we will discuss this source with unidirectional cosine square pattern. So cosine square pattern means, as I have told, that in place of you have to substitute cos square theta. Okay. So here I have substituted u is equals to cos square theta. Now as the procedure says, you have to find out the power. So first of all you need to identify the power as P is equals to surface integration intensity into d omega. D omega is the solid angle. Okay. So in place of u, substitute cos square theta. In place of d omega, substitute sin theta, d theta and d phi. You will, after solving this, you will get around 2 by 3 pi into So this is the value what we will get with respect to the cos square theta pattern. Okay. Now we have to compare with respect to the isotropic pattern, because we are considering that point source is isotropic in nature. We will compare that one so that the relative value will give us the directivity. Okay. So that relative value is, for isotropic antenna we have 4 pi into u0. Equate this to power. It is 2 by 3 pi into divided by 4 pi u0. If you take this relative value by u0, you will get around 6. Okay. Okay, remember these relations, remember, because these are constant. The questions may ask about these patterns, power pattern. If the cosine square terms or sine square terms, you have to derive all these things, you have to solve it, and you have to form the relation. So here, if it is square cosine square unidirectional, that means the pattern will come like this. So theta is equals to 0 degree, and here it is maximum value, and this is your um divided by u naught. So this is your u divided by u naught divided by u naught. So it is 1 by d. Okay, so that directivity we have to calculate. So like this, if any sort of question is given, it is very easy to approach it. Okay, so next class we'll discuss about the field pattern. Today we have discussed about the power pattern. Next class we'll discuss about the field pattern, and then we will see the array, points of array. The sources will be in a certain arrangement, and we have to see what is the effect is going to be seen. Okay, and then the first part of the module 4 will be over. Next part is the type of antenna is there. That is quite easy, derivations are there, and according to that we can wind up this session. So for the today's session, thank you.